Yeah, I'm very glad. Yeah, there's
Okay. Good morning, everyone. Let's get started. So first of all, please be aware our due of homework 1 is coming. So I guess it's this Friday. I ask you guys to implement the decision tree learning algorithm and test it on 2 data sets and show the effectiveness. So I'm saying some students already started doing that in my office hour. That's good, right? If any of you haven't started, please start it right away. Right? You do need some time to check your algorithm implementation is correct, and sometimes you do need some time to debug your code. And second thing is that we're going to release assignment of project selection. Right? So what you need to do is make a decision what type of project you want to do. If you're doing exploratory project, right? You're doing some research. If you want to form a team, let us know what's your teammate, right? So our TAs will record your project selection. I think the due will be next Friday. So you got one week to make a decision. And last week we released the Kaggle competition. So I guess we got enough time for you to experience the setting of the competitive project. So it's time to make decision now. And later I'll ask you guys to submit your project proposal and the midterm project report and then the final. Okay, any question? Oh, sorry. Okay, yeah. That's my fault. But again, I highly suggest you guys to do it right now. Right? Don't start doing like at last day. It won't succeed. Any other questions or concerns? Yeah, again. Can you say again? The first attribute, what? Uh-huh. Uh-huh. I think that depends on the problem description. If the problem description tells you that, okay, we got the attribute list and what is the value range for each attribute, like then you look at table. If some value doesn't show up in the table, well, we have to create some virtual branch, right? But it doesn't, like you can by default use the value showing up in the table as your value range. Does it make sense? No, I don't think information gain is related to like whether you got a missing value, whether some value doesn't show up in the table. Because if it doesn't show up, you just calculate the so information gain is calculated based on the existing values, right? So you if some value is not taken, you create a branch, you take the majority label as your leaf nodes label, right? That's not counted as inside information gain because you don't have like a set of examples. for that. Yeah. I mean, we can talk about details later, say in the office hour. But yeah, it's good to ask question about that, right? But here I just want to emphasize that everyone needs to pay attention to our schedule, right? Homework 1, according to our past experience, maybe psychologically the most challenging one, because you need to get used to this style, right? Homework 0 is like, okay, you just review your textbook and try to get familiar with those knowledge you have learned before. But homework one is really something, I mean, inside this class, right? You need to make sure, you understand the details of algorithm. You need to make sure you correctly implement this algorithm and debug in the real data set. So it's always better to do it early. And also it's always good to leverage our office hours. Okay. Okay, great. So let us continue. In the last lecture, we talked about several variants of information gain, right? So so basically, we want some metric to measure the purity of the labels, right, in a data set. So entropy is a good choice because it is underpinned on the information theory. It's very wide used concept. So entropy reflects the purity, right? High entropy indicates low purity. On the other hand, low entropy means lead to uncertainty means like high purity. The reduction of entropy reflects the improvement of the purity. That's how the information gain is defined, right? So we calculate the entire data set's entropy, and then we calculate when we use one particular attribute to split on the data set, what is the weighted average of the entropy over each subset, and then we calculate the difference between the two, right? Then we can measure how much purity we got improved after we use that attribute for the splitting, right? So, but entropy is not the only metric that can be used to measure the label purity, right? We introduce additional 2 variants. One is called majority error. The other is called Gini index. Actually, in practice, Gini index is even more popular than the information gain. It appears to be more robust, right? But basically, their idea is kind of similar. They use some kind of metric to measure the purity, and then they calculate the reduction of those gains, those metrics to reflect improvement of the purity, right? So that's why the whole framework is the same, except the only difference is in how you're gonna measure the label purity, right? So if you started doing homework 1, we'll ask you to implement different variants of information gain, right? So actually, it's very easy to implement as long as you have a good understanding of those different metrics. Okay, and then we'll talk about how do we handle the incomplete examples in both training and test case, right? So in the training case, like if some attribute value is missing, right, the most straightforward way is to complete it with some guess, right? We can use the most common value of that attribute in the data set to input that value, right? Or we can use a more elegant approach, right? We can break this incomplete example into several fractional examples, right? So that for each different fractional example, we're going to impute with a different attribute value. In this way, we can consider all the cases, right? And the only difference is that how you're going to calculate the count of each fractional example. It's no longer 1. It could be like 4 over 14, 5 over 14, and 6 over 14, something like that, right? But the calculation of entropy or Gini index or all the other things is exactly the same. What we need to do is just when you count the size of the data, you need to add this fraction count, right? When you calculate the number of positive examples, or the number of negative examples, you have to add this fraction count, and all the others are the same. So don't get confused or feel lost about that. There's nothing difference in essence. Okay. And then we'll talk about how do we reduce the branches of the decision tree, right? For example, some categorical feature has a large number of possible values. You don't want your tree to grow too wide. You got 1,000 branches. So how can we do that? We can convert those multi-class features into a set of binary features. Right? So we can see like if overcast can, no, sorry, it's not overcast. All can take 3 possible values: overcast, rain, and sunny, right? And then we can convert it into 3 binary features, whether your all look is overcast or not, right? Whether your all look is raining or not, or whether your all look is sunny or not, right? So this is a commonly used way to make your tree to skinner, and also later we'll talk about how do we make our train to be shallow. And overall, our goal is to restrict the growth of the tree so that it won't overfit. Right? So now comes to the key concept. What do we mean by overfit or overfitting? Right? This is a very, very important concept in machine learning. Perhaps once you have heard machine learning, you heard overfitting in the meantime. Right? But what does overfitting mean? Right? Before we give a formal definition, we want to start with a concrete case. So suppose this is our task. Right? We want to learn a balloon function, and this balloon function is determined by binary features. So it means that I got a set of features. Each feature can take either 0 or 1, right? And the function value is also true and false, means 0 or 1. Right? So here's one example, right? Suppose this is I want to learn a balloon function of 2 binary features, right? So obviously, this function can be represented by this table, right? So it contains every combination of the values of these 2 features and corresponding function value, right? And if we have this table as our training data set, right? We throw it into our decision tree learning algorithm. So the tree will look like this, right? So this function is called first bit function, meaning that the function value is solely determined by x0, right? It has nothing to do with x1. So when you construct a tree with your ID3 algorithm, it will smartly choose the first feature x0, and then you end up with 2 subsets, and turns out their labels are unique, so you end up with 2 difference. Okay? So I suggest you guys to manually verify this, right? But this is the result. Everyone is good? Okay. So now I want to give a conclusion. In fact, for arbitrary balloon function, right, it's not like only this special first bit function. For arbitrary balloon function, right, with n binary features, if you can fit these whole tables of feature values and function values as the data set to train your decision tree, this tree can perfectly learn this balloon function. What does it mean? It means that, okay, if you use that data set to train your decision tree, and then you test the decision tree with any combination of those feature values, it will make exactly correct prediction to the function value. Why? Any thought? Oh, go ahead. Mm-hmm. Mm-hmm. Yeah. you he expressed exactly the same thing he want. Yeah. Well. Mhm. Yeah. So you are correct. Let me summarize. Okay. So this fact actually expresses the power of decision trees, right? So remember, decision tree for the ID3, if we do not modify the algorithm, we just keep growing the tree until we reach some leaf node where all the examples on that leaf node has the same label, right? So you can see that in the worst case for some Bloom function, right, you're gonna exhaust all the n Bloom features, right? Like once you exhaust all the features, you at least end up with one function value, right? And it must be unique labeled, right? It either true or false, right? And in other cases, it might be okay. I haven't exhausted all Bloom functions. I end up with some subset of examples. They give the same function value, and then stop, right? But even in the worst case, it can enumerate all possible combinations of the feature values, and then it will give you a unique labeled function value. It's actually either true or false, right? So that's why if you can fit the decision tree, the whole table about these function values, it will perfectly learn that function. And now if you use this any row of that table to test your decision tree, it will give you exactly what is the function value, right, in the prediction. Everyone agrees with that? Okay. So suppose we have all 2 to the power of n examples for training, right? Because each feature takes 2 possible values, true or false, right? If you have n features, then your giant table will have 2 to the power of n examples, right? And what will be the error on any future examples? I heard that, right? 0, right? Because you have seen every possible input, your training set, right? So if you pick up, you haven't seen every row, which correspond one possible combination of those feature values, right? Now, your test case, right, your test scenario, the range of the feature vector won't exceed the range of the training table, right? So you must pick up any one row of that table. Now you use that to predict, right? It will definitely recover the original function value. So what does it mean? It means the decision tree can represent the function exactly, and the ID3 algorithm will build a consistent tree. Consistent tree means that your tree will be 100 consistent with the training data. In other words, if you use your tree, your learned tree to predict the training examples, your training error will be 0. Right? So this is our like foundation based on which we're going to discuss next. Everyone is clear about that? Okay. So here's the problem, right? If your training data are great, are perfect, your test data are great, are perfect, looks like such kind of like perfect fitting is nothing wrong, right? It's good, right? Because I can guarantee your test error is 0, right? However, in practice, the data in most cases are not perfect, right? They're often noisy, contained or corrupted, and then contain mistakes, right? So in that case, let us try to analyze what will happen, right? If my tree has with my tree's like perfect ability to fit data. So we're gonna still use a simple example, right? So here we will assume that the outputs of the training test sets are random corrupted. We're not assuming we're going to random corrupt the feature values. Let's just assume, okay, there's some kind of random noise which corrupt the labels in both training and test sets. Okay. So that means each label in the training set has some chance to be flipped. Right. Similarly, each label in the test set has some chance to flip. Then what will happen? So here are some experimental results. So this, what does this figure tell us, right? So the x-axis shows the number of features, and the y-axis shows the test accuracy for different input size. Right? And this arrow bar shows, like, because I want my results to be stable, so I run this experiment multiple times. I calculate the mean, test error, and standard deviation. So the arrow bar shows the standard deviation. So remember, when we increase the number of features, then the size of the training data grows as well, right? Because remember, we use the whole table, which contains all combinations of feature values and their function values as a training set, right? So the table size will be 2 to the power of n examples, right? So of course, when we increase the number of features n, the size of the training data get larger and larger again, right? So you can imagine that the training, the performance get more and more stable. So now we can observe that the test accuracy or test error is kind of convergent, right? It converges to be approximately 0.375. Okay, so I want to ask why we no longer say 0 test error. What's the problem? Yes, right. Any other one who wants to add more comments? Yeah. The critical change of the settings here, right? So if training set and test set are the same, right? Are complete or same, that's the ideal case, right? Of course, you have 0 training error and 0 test error. But now, my training labels and test labels are both random corrupted, right? So that means the training set and test set are no longer consistent. However, your decision tree learning is still 100% fitting the training set, right? So that means if you fit a wrong label in the training set, you're going to make wrong prediction in the test case, right? So this actually can be analyzed by simple statistics, right? Let's do it together to have a more thorough sense, right? So when will our learned decision tree make correct prediction? 2 cases. Yes, right? So for the same training or test example, right? So that means the same particular combination of the n binary feature values, right? If their label in both the training set and test set are not corrupted, right? They remain the same. Of course, my prediction will be correct because in the training phase, I'm gonna give that prediction and for that label, right? And doesn't change during the test set, so I'll give the same label, so my prediction must be correct, right? Or both labels are corrupted, right? Are flipped, right? So they're supposed to be positive, right? But in both training and test set, for the same input example, their labels are flipped into negative. Because my training procedure will guarantee my decision tree is going to predict as negative, right? In the test set, I'll predict the same example as negative as well. So my prediction will be correct as well. Does it make sense? Right? So here our assumption is that those random noises are independent. So we can just add up the two probabilities, right? The first probability is that both training example and test examples are uncorrupted, right? So each example, they got 0.25 probability to get corrupted. So the probability of uncorrupted is 0.75, right? So multiply 0.75 times 0.75. This is the probability of the first case, right? So the second case is that for the same example, their label in the training set and test set are both corrupted, right? So the chance will be 0.25 times 0.25. So if you add the two probabilities together, it will give you the total probability you give correct prediction as 0.625, right? And accordingly, your wrong prediction will be 0.375, right? You just subtract 1 by this probability. Does it make sense? Any questions so far? Great. So similarly, we can directly analyze the probability you make incorrect prediction, right? So when will we make incorrect prediction? When? Yes, exactly, right? So when for the same instance, right, their training label is different from its test label, then you must make wrong prediction, right? So when their labels are different, only two cases, right? Training label get uncorrupted, but test example get corrupted. Or training example is corrupted, but test example is uncorrupted, right? So for each case, the probability will be 0.75 times 0.25, right? One is corrupted, 0.25, the other remains unchanged, will be 0.75, right? You just add them together, it will give you the total probability of incorrect prediction, 0.375. Okay. So then the question is, what about the training accuracy? The same, right? Yeah. Yeah. So, I mean, we're not talking about, okay, the exact rightness of the label, right? We're talking about, okay, if I train with this data set and their labels, right? And then we test it on the data set with their labels, right? Are they consistent? If they are the same, okay, you'll make a correct prediction. If they're different, make wrong prediction. Okay. Yeah. Now I want to ask, like, now if after I learn the decision tree from this training data, right? If I test decision tree with the training data, what's the accuracy? Now here, the difference is that I'm not gonna test my decision tree with the test data, where the labels can be changed, right? I just use my training set to test. Yes, it still be 100%, right? Remember, the decision tree can learn arbitrary Bloom functions, right? Even your labels get corrupted, it still corresponds to some Bloom function, right? It can perfectly learn that Bloom function. That means if you test your learn decision tree on that particular corrupted training set, it will still give you 100% accuracy. So, but here there's a huge discrepancy, right? So we still get 100% training accuracy, but my test accuracy decrease, right? Decrease a lot. It reduces to like 62.5 5% accuracy, right? It's a huge drop. So what's the problem? Where's the issue in essence leads to such a big gap? What? Yeah, it's overfitting. But why this overfitting is bad? Mm-hmm. 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 Yeah. Your point is definitely correct, but can we use even more straightforward language to explain that? Mm-hmm. Yeah, you guys talk about the generalizability, right? And we know that if training set is consistent with test set, this is nothing wrong, right? However, something happened, makes this hard coding or whatever perfect fitting of this training data generalized badly to the test set. What's that reason? Doesn't matter what? The population? That's a little bit we want to be a little bit more explicit. Yes, exactly, right? So I don't know if it's a noisy statement is connecting to your population, but here's the case, right? Because your training data is no longer perfect. Your training data is corrupted with noises. But the decision tree learning is still very powerful, right? It still perfectly fits the training data. And as a consequence, right? The classifier also fits the noises in data. Right? That's why we call it overfits, right? Actually, we just want to fit those useful information or knowledge in the data, in the training data, so that we can generalize well, right? But if we happen to fit the noises in the data in the meantime, then it can break your ability of the generalization. That's the case. So what's the bad effect of overfitting, right? The learning algorithm fits noise in the data. Those noise data, I mean, in our example, it just contains the label noises, right? But actually, irrelevant attributes or noisy features can also lead overfitting as well, right? So those noise fitting can influence your choice of decision tree. And in most cases, unfortunately, it will make your tree worse in the generalization performance. Right? That's why people do not like overfitting practice, right? Because it can lead to poor performance on future examples. Right? However, in the ideal case, like if your training data is perfect, doesn't contain any noises, and is purely useful information, overfitting is a good thing. It's not bad. Right? But in practice, like practical world is not perfect at all, right? It always has this deficiency, that deficiency. You got missing attribute values, got noisy or incorrect labels or all kinds of stuff, right? You cannot 100% trust your training data. But now, if you feed them into a very powerful algorithm, it not only absorb the useful information, also fix all the noises, and those noises, unfortunately, will lead your learned model perform badly. That's the issue, right? Any questions so far? Okay, great. So now let us take a look at the practical evaluation of the overfitting, right? So it's not some simple synthetic experiment, right? So this is a graph I steal from a classical machine learning book written by Tom Michel. Right. So in that book, it shows when you grow the tree as larger and larger, what the training accuracy and test accuracy varies. So here, the training accuracy is this black line, and the test accuracy is this dashed dotted line. Right? So the x-axis shows the size of tree. So you can imagine that it kind of like hard stopping the growth of tree according to the size, right? And you can imagine that if we do not restrict the tree growth, right, I can grow as deep as possible, so I can grow as large as possible, right? And we can see that, like, see the trend of these two curves, right? Training accuracy and test accuracy. First, for the training accuracy, right, you can see that as the growth of the tree, right? Question? Fit to the training data. Yeah, because here we're not talking about learning a balloon function. It's just the fit to the training data. And the test data, you can view as large test data, right? So you can see that when you grow the tree, continuously grow the tree, the training accuracy keeps improving, right? So meaning that it get better and better fit to the training data, right? But what is the change or variation of the test accuracy? What can we observe? You can see that at the beginning when you grow the tree, right, it keep increasing, right? But at some point, right, some turning point, right, when you continue to grow the tree, the performance starts to drop, right? So that's a typical phenomenon of overfitting. So at the beginning, if your tree size is too small, I mean, the model is too simple, right? It's not capable enough of capturing those relationships, right? And make correct predictions. So increase the model complexity appropriately. That's doable, right? That's okay, right? However, when the capacity of model, when the complexity of model grows to a certain size, right? If you keep doing that, then your model kind of like overfit the noise in the data, right? And as a consequence, your generalization performance starts to decline, right? Starts to drop. Right? That's why in practice, like not only for decision trees, right? For deep neural nets, people always like have some technique to trying to find out overfitting early, right? And there's some trick, it's called early stopping. They use some validation set, right? And every time when they go through the training set, like for several epochs, they're gonna test the accuracy on the validation set. Once you see the decline, performance decline, the validation set, they're gonna stop training. Why? Because they want to avoid overfitting. Okay. So now, how can we avoid overfitting the decision trees? Right? The strategy is to restrict the tree size. Right? I don't want my tree to grow arbitrarily large. Right? So the most straightforward approach is to fix the depth of the tree. Right? This is the simplest approach, right? So I can just add one additional variable, right, to record what is the current tree depth, right? Once you have reached the maximum tree depth, you just stop growing and you create leaf node, right? Even the corresponding set of examples are now purely labeled. I just stop. I just assign the leaf node with the majority label. But there's some like extreme case, like you can simplify a tree. Like, see, I only allow my decision tree to grow one level, right? So this tree is called decision stump. And this is very useful when we do the ensemble learning. So later we'll talk about the bootstrap, ADA boost algorithm. They're constructed by a set of very simple or oversimplistic classifiers like this, like decision sum, and then you smartly combine together, you end up with a super powerful model, which not only like expressive enough to represent those complex functions or relationship, but also it can well fitting. Okay. But we'll talk about that later. So this is the first strategy, fix the depth of tree. And second one is kind of like a more dynamic, right? It's similar to the early stopping trick we just discussed. Right? We're gonna separate out a portion of the data, right? We call it held-out set or validation set, right? And now we're gonna, when we grow the trees, we're gonna monitor the performance on the held-out set, right? So we use the performance on held-out set as kind of a surrogate or approximation of the generalization performance, right? So every time when you grow a tree, right, you create new branches and the nodes, right? You're gonna test whether on your held-out set, your current tree will increase the performance, increase the accuracy. If it increases, okay, you're fine. You just leave your new branches nodes there. Otherwise, it turns out that the growth of the tree leads to the decrease of the accuracy on held-out set. We're gonna stop growing. Right? We're gonna throw out the new branches and nodes. That's the whole procedure, right? So both the you fix the depth of tree, or you dynamically decide which branches or nodes you're going to create or which not, are kind of like you're generating the tree and you decide whether you're going to stop, right? So there are some other approaches called post-pruning approaches. We can try to grow the full tree first, right? Let us try to grow the tree as large as possible, as deep as possible, right? And then I try to prune as many as branches after the tree has grown, right? And usually you're going to use a validation set for pruning from a bottom to up with another greedy heuristics, or you can convert the full tree into a set of rules. You mentioned that every pass from the root node to the leaf node forms a prediction rule, right? So you can decide which rule you're going to cut and throw out. Right? So those are basically three commonly used strategies to control your tree size. Validation set. Okay, so if you have say 1,000 training examples, right? So if you want to use validation set, you have to sacrifice some training information, meaning that, okay, I can random pick up 100 examples, pick them out from a training set. I use this 100 example as my validation set. Then I only train my decision tree learning on the remaining 900 examples. And every time when I grow a tree, right, and I create several new branches and I know several nodes there, and now I test my current tree on these 100 examples, right, to look at the prediction accuracy. If the prediction accuracy increases, that means, okay, my tree growth seems right. I just keep my branches, and then I start to consider splitting the nodes under those branches. You keep doing this until at some stage you say, okay, I grow this tree, I grow new branches and nodes, and I found out, okay, the test accuracy on that validation set starts to drop. Then I stop. Yeah, that's one option. I mean, here we just give a general idea. I mean, if you want to do that, okay, you can decide to test every possible node, or you can decide test after level 2 or after level 3. It's up to you. But this is the basic idea. You have a question? Yeah, you can do that for sure. Like someone said, okay, I believe that maybe the number of examples is too small. It's not statistically reliable for me to stop. I should grow the tree, or I should grow the tree and more. It's fine. That's another stopping criteria. Other question? Okay, great. So so far we have finished the discussion about decision trees, right? So overall, decision tree is a very popular, very classical machine learning tool, and there are not too much research, cutting-edge research on decision trees because it has been very, very mature, right? But it's still very widely used, right? So in your future, right, if you want to use machine learning tools to address some problems, right? If you do want some high transparency and interpretability, you might first consider decision trees. And also in many cases, like some variants of decision trees, like reading, boosting decision trees are still state of the art. Right? And also very fast. You don't need to buy 1,000 GPU units, right? Train a single GPU, like instant fast. Right? Since prediction is easy, it's very expressive. And the ID3 algorithm, we introduce the recursive programming of the ID3 algorithm, but you should understand the nature of this algorithm. Essentially, it's a greedy heuristics, right? So every time, based upon the previous attributes used for splitting, right? I want to pick up from the remaining attribute who is going to best improve the label purity, right? I do this best local decision, right? And to expect that, okay, after a few number of the steps, right, my trees can stop growing, right? And also, although you're not gonna require to implement some regression tree, but just be aware that you can also use tree to do regression, right? And decision trees are prone to overfitting, right? If you do not restrict the size of tree. So you need to take care of avoid. A typical strategy is to fix the depth of tree or find out, use like a separate validation set to control the tree growth. Okay, any questions so far? Great. Next, we're going to talk about several basic concepts in computational learning field. Right. A very brief introduction. So it was motivated by the concept of overfitting, right? So we're going to give a more formal definition of overfitting, and in this basic concept over the umbrella of computational learning theory. But don't worry, this is not a theoretical course. We won't spend too much time on theory, but we do need everyone to have a sense about those basic concepts because these are really important concepts, and it will motivate our subsequent algorithm, like support vector machines. So you see that the most important concepts in the learning theory is the empirical error and the generalization error. So you see that a lot of content, I guess the majority of content in computational learning theory is about like how do you use the empirical error to estimate or bound the generalization error. Right? Because if you want to know like how well your learning algorithm performs, right? You want to know what is the generalization error. But later we'll see that you won't be able to get generalization error. Right? And what we can get is a so-called empirical error or the training error. So, I mean, if you want to estimate how well your algorithm performs, right? We need to figure out the connection between the empirical error and generalization error. Right? Then we'll define the so-called PAC learnability. probably, approximately correctness. It's a very lengthy, tedious definition, but only using that, you will see later, right? Only using that definition can give you some rigorous characterization about which learning algorithms are efficient, which learning algorithms not efficient. And then we're going through a simple analysis to make a formal connection to the principles of Occam's reasoning. Okay? So we mentioned that in decision tree learning, we favor the most succinct tree, the smallest tree, right? We just tell you, okay, this is some kind of principle we should believe in, right? But why? Okay? Can we have some justification? Right? And in the computational learning theory, we can make such kind of connections, and we'll see that connections later as well. But before we proceed, let us just step back and do some retrospect review of what we have seen so far, right? So here's a bigger picture, and we have talked about the supervised learning framework, right? We know that if we want to do supervised learning, we need to prepare the training instances, right? And we should prepare the labels, right? Also, we need to consider what is the possible hypothesis space, right? And our learning algorithm essentially is to use the label, the training data, to search a hypothesis from some hypothesis space, right? We find the best one, we consider that as our learned model, and use that to make a prediction, right? That's the whole procedure, right? So under this framework, we're going to discuss a list of specific learners. The first one we have finished introduction. It's called decision trees. And later we'll talk about perception. We'll talk about least mean square regression. We'll talk about boosting. We'll talk about random forest. We're going to talk about support vector machines and so on. And also we have through the introduction of decision tree, we have discussed the phenomenon of overfitting, right? And also we know that overfitting is not good in practice because the data always contains noises. Overfitting will make your learning misled by the noises. Okay, now let us give a deeper understanding about these basic concepts with computational learning theory. So what does this computational learning theory care about? So let us consider we got a machine learning model, right? Or machine learning algorithm, whatever, right? We have trained our model on some fixed training set. Then we want to deploy the model in the wild. That means I might pick up any test instances and to look at its prediction, right? Then the computational learning theory likes to know, right, how well the learned model performs on the future instances. Okay? That is called generalization performance. Okay? So now let us define a set of terms or jargons to get us easier for the discussion, right? So in a supervised learning setup, we need to define a space called instance space, right? Instance space we discussed before. It's just a set of possible examples, training set or test set. Right? And then we're going to introduce a space. It's called concept space. So what does concept space mean? It just means the type or the family of the target functions. So what is the type of their underlying ground truth function you want to learn? Like for example, maybe your concept space is just balloon function family, meaning that your target function is just a balloon function, right? Or maybe your concept space is n-dimensional linear functions, right? And then your target function is just one member of that function, right? It just gives the range of the target function you want to learn. And then we introduce the so-called hypothesis space. Remember, our learning essentially is a searching procedure, right? And every learning algorithm needs to specify the range of the possible functions you want to search over, right? So the hypothesis space is such a range, right? And here I want to emphasize that the concept space and hypothesis space do not necessarily overlap, right? Sometimes you even do not know what your concept space is, right? But what you exactly know will be the hypothesis space. For example, if you're running a learning, if you learn a linear model, you know, okay, your hypothesis space must be a set of linear functions or linear models, right? But your concept space, you might even do not know whether your target function is a linear function or nonlinear function. And also, you got a set of training instances, right, or training data set, right? So this S is just a finite set of examples, right? And the labels -1 and 1 here, we just assume we're doing binary classification problem, right? So the training instances are representing the pairs of the instance and their label. Okay? The label is labeled by the target function. So here's the basic concepts associated with supervised learning. Right? What do we want our learning algorithm to do, right? We want our learning algorithm to find out a hypothesis, small h, from a hypothesis space, and such that the prediction made by the hypothesis is consistent with the prediction made by the target function, right? But here, regarding the consistency, right, we got like two levels of consistency. Right? The first one is that your learned hypothesis is consistent with the target function on the training set, meaning that for every training example, the prediction made by H is the same as the prediction made by F, right? That means you got 100% training accuracy, right? And the second level actually is the ideal case, right? We want your learned hypothesis is consistent with your target function for all possible instances in the instance space. This is the ideal case. And in most cases, right, we can expect that our learned hypothesis satisfy the first level, right? It can get consistent prediction with the ground truth target function on the training set, right? But we're not able to claim that they're going to be consistent for all the instances in instance space. Does it make sense? Those basic settings, right? Okay. And a very important assumption here, right, we're going to make is that we assume the training instances are generated by some fixed unknown probability distribution D over the instance space X. Right? It's like, okay, if your task is to recognize faces in the images on the web, right? So you got to know, like, there are tons of millions of images generating in the web every second, right? They are generating from some underlying complex mechanism, which you do not know. Right? And so assume that, okay, the generation can be described or characterized by some fixed unknown probability distribution. This is a very general and reasonable assumption. So in task procedure, we're going to assume that, okay, the task instances will be generated from the same distribution. Right? And then we want to evaluate our learned hypothesis H on subsequent task examples, which are joined from the same data distribution D. Does it make sense? Right? Here we just assume, okay, there are some unknown data distribution D, right? We do not assume we know what is the form of distribution. You may not be able to even write down any closed form for that distribution. Okay? But we assume there is some underlying distribution that generates those instances. Okay. So now, given those settings, we have our definition of the generalization error. Right? So what's the generalization error? For any hypothesis H, right, its generalization error with respect to a target concept F, okay, is defined as the probability that the prediction made by H is different from the prediction made by F, where the input instance is drawn from the data distribution D. So you can see that it's just a simple probability that you make wrong prediction, right? But the input instance over which you make prediction is drawn from this unknown data distribution D. Right? So you can see that the generalization error is not only related to H and target function F, it is also decided by the unknown data distribution D. So now if we want to give a concrete or intuitive view of the generalization error, right? And suppose this is your instance space X, right? So remember there's an underlying distribution D defined on this instance X is big rectangle, right? So maybe the instances here will have less probability density than the instances here, right? It depends on D, right? So here, this blue ellipses are all the positive examples labeled by my target concept F. Okay? So those are the positive examples labeled by F, and the remaining examples are labeled by or negative examples labeled by F. Right? And suppose you got a hypothesis, right, which is found by your learning algorithm, right? Your H can label the instances in the instance space as well, right? And here, the second ellipses are the positive examples labeled by your hypothesis. So you can see that they're not consistent, they're not totally matching, right? So there are some kind of overlapping. Right? So the error comes from here and here, where the labels of made by F and labels made by H disagree. Okay? So the generalization error actually is the area of those disagreement region, right? And remember, you have distribution and probability density over examples on these two regions, right? So you're gonna integrate over those two regions to get your area. Does it make sense? Right. This is what the meaning of the generalization error. So now I want to ask, right, from a practical perspective, right, are you able to calculate this generalization error? Can we do that? Why not? Yeah. Yeah, I'm not talking about something. I mean exactly calculate that. I'm not talking about approximation or estimate. Why? Okay, yeah. Yeah, that's one important observation, right? So actually there are two things, right, which make in practice were literally impossible to calculate the generalization error. I mean exactly calculate, not estimate or approximation. Right? First, you really don't know what is the ground truth F, right? You don't know that. And in many cases, you even do not know what is the concept class. I mean, what type of function, what type or what family this target function belongs to. Right? You don't have the golden standard, you don't have the oracle. How do you know how to calculate that? The second thing is also equally important. You usually don't know the data distribution D. Right? It might be easy to get a sample from that. Going back to the face recognition task we just discussed, right? It's very easy to find a image or download an image from web, right? But you'll never know what kind of distribution that generates those images, right? So you can see that those problems make us, like in practice, basically is infeasible to get exact generalization error, right? But then the problem is how do we evaluate the performance of our learned model or learned hypothesis H? Right? This is something we're really concerned, right? We want to know, okay, how well it performs. The strategy, more practical strategy, will be some kind of estimate. So the most common used estimate is called empirical error. Right? What does empirical error mean? This is lengthy, it's formal lengthy, but I'm going to replace it with just 2 words: training error. Empirical error is just training error. So basically, once you learn the hypothesis H, you test H on your training set and say what is the error you get. We call it empirical error. Like, so we denote empirical error, that is error S, right? S, because S denotes the training set, right? And we denote this generalization error by error D, because it's determined by the data distribution D. And unfortunately, we do not know what D is, right? Now, given these definitions, right, we can give a more formal definition of overfitting. That is, when the empirical error on the training set is substantially lower than the generalization error, then we call your algorithm or learning model is kind of overfitting the data. Does it make sense? Any questions so far? Okay, great. So now let us merge the list of symbols and notations, right, to get our formulation of computational learning theory, right? We use big X to represent the instance space. We use big Y to represent output space, and here we're doing binary classification. We use big D to represent or denote an unknown data distribution over X. And we use small f denote the target function, which is mapping from the instance space to the label space. And f comes from the concept class C. And we use small h to represent a hypothesis function. This hypothesis is found by our learning algorithm and search from the hypothesis space or hypothesis class big H. Right? And we use big S to represent a set of M training examples, which are drawn from the data distribution D, and the labels are labeled by F. Right? And also we define 2 very important fundamental concepts: the true error or the generalization error for any hypothesis H, right? And the empirical error or the training error. Sometimes people also call it observation error, right? That is, if you use H to test or to predict the labels on the training set, what is the error, right? So given those notations, or given those definitions, right, what kind of problems are we interested in? Right? The first one is, can we describe or bound the generalization error by the empirical error? Right? As we mentioned, as we discussed, right, the generalization error is so hard to get, right? So the only feasible way is to use some observation error to make some approximation, right? Or even get some upper bound or lower bound can help us better understand the generalization performance of our learned model. Right? And the second thing is even more fundamental, right? For this particular type of target functions, are they learnable? That is, for any concept class C is learnable, right? And then here, what do we mean by learnable? And later we'll talk about that. Right? And third one is that to guarantee some good performance, to reach some good performance, right? How many training examples would you like to use? Of course, we don't want too many examples, right? Because it will largely, then our computational and memory will have a severe bottleneck, right? And fourth one is more related to computer science, right? How much cost does an algorithm take to learn some type of target functions? Right? If it's too complicated, right? It's too costly, say NP hard, of course, it won't be feasible, won't be practically useful, right? So computational learning theory tries to address those for problems. But before that, we need to define, right? What kind of what do we say? What do we mean by a good learning? Right? What kind of expectation should we take for a learning algorithm? So first, I want to ask, right? Can we expect our learning algorithm to recover a target function exactly? No. Why? It's impossible. Why do you think it's impossible? Yeah, I think you covered some pretty points, right? I mean, we're considering this problem in a practical point of view, right? So first, remember, learning is conducted by fitting some finite training data set, right? So that means as long as finite, right, there could be many different functions exactly fit the same finite number of examples, right? So that means literally it always impossible for you to identify the target function, right? Exactly, right? Because there could be multiple choices and each choice is equally well, right? Of course, you got some like principles like Occam's razor principle to pick up the best one, but it's not guaranteed that it will be the truth, right? So here, we agree to misclassify some uncommon examples that do not show up in the training set. It's still because of the finite training data issue, right? Your whole instance space, in many cases, it won't be discrete. It could be continuous, right? That means no matter how many examples you draw, you won't be able to cover the entire space, right? So it's possible that for some uncommon examples, they will never show up in the training set, you make mistakes. So in that case, we first need to give up the expectation that, okay, we require our algorithm to learn a target function exactly. And second thing, right, we step back, right? Can we always expect our algorithm to learn a close approximation to the target concept? Would that be feasible or reasonable requirement? Okay. Any thought? Unfortunately, this is not released as well. So don't think machine learning is is super powerful. It's not that powerful. Yeah, it's not powerful. Why? Because the learning performance is not only determined by algorithm itself, right? It's also up to the quality of your data. Our training data are just collected from some unknown data distribution D, right? They're random. They essentially are random variables, right? So you cannot guarantee you always get a high quality training data. It will represent the whole instance space and data distribution so that your learning algorithm will always return you a close approximation to the true of the true function, right? It's possible that, okay, in this in experimental one, you get a set of training set, very good, high quality, you get very good approximation to the target function. Next time, you might get a collection of garbage, right? It's possible. I mean, it's possible, right? Especially when your data set is not large, right? In that case, even your algorithm is perfect, right? Your algorithm is very good, very powerful, but garbage in, garbage out, right? It won't give you, you can end up with a very bad hypothesis. Yeah, that's a very good question. That's actually the question the computational learning theory tries to answer, right? We'll see that sample complexity bound, those kind of stuff are trying to give you this answer. Right? So we can see that, okay, actually when we want to analyze the possible performance or possible expectation of the performance of your learning algorithm, we found is highly restricted, right? We cannot expect a learner to exactly learn the target concept. Even we cannot expect a close approximation. Then what is the realistic expectation? The realistic expectation is that with high probability, our learner can learn a close approximation to the target concept. Why? Because the data, the training data is random, right? You cannot guarantee like 100% every time it will give you a good approximation. Right? You can only expect that if your algorithm is good enough, you should say it has a high probability to give you a close approximation to the target concept. Right? And then most of the theories in computational learning theory are built upon this expectation. Right? So giving you some high probability threshold and generalization error threshold. Can this algorithm use not many examples to find you such a hypothesis? That's their idea. Does it make sense? So next we can introduce the concepts called probably, approximately correctness, right? So shorted as PAC learning, right? So what is PAC learning, right? PAC learning actually is a criterion which differentiates those efficient learning algorithm and inefficient learning algorithm. An efficient learning algorithm basically means to arrive at this bar, right, with high probability, find a good approximation to a target concept. It doesn't need too many training examples. And how many training examples does it need? It just needs to a polynomial order of examples relevant to your given probability threshold and generalization threshold. Right? That's called PAC learnable algorithm. Right? And for the other algorithm, it means that, okay, it might use too many examples to achieve the same level, right? A same probability bar. And then those algorithms are not considered as PAC learnable and they're inefficient. So that's the key idea of the definition PAC learnability. Okay. So keep that in your mind. Let us walk through the definition. Right? The definition is a bit lengthy, but the key idea is here. So we're going to use some small parameters, epsilon and delta, to denote the probability level and generalization error level, right? So when we state this more rigorously, we're going to state as with probability at least 1 minus delta, the learned hypothesis will have a generalization error at most epsilon. Say, if I specify epsilon to be 0.05, delta to be 0.05, that means with the probability at least 1 minus 0.05 means with the probability at least 0.95, your learning algorithm will produce a hypothesis with generalization error at most 0.05. Right? That's a quite strong statement, right? So now let us look at the definition of PAC learnability, right? We consider a concept class C, a type of target functions, defined over the instance space X, and also assume the instance are represented by n-dimensional feature vectors. And we're going to use a learning algorithm L to find the hypothesis from the hypothesis space H. Right? Then we see that the concept class C is PAC learnable by our algorithm L using hypothesis space H if for every target function in this concept class, and for every possible distribution D defined on the instance space, and for every possible probability level and error level, you only need a polynomial order of a number of examples in these guys, your learning algorithm L can find a hypothesis which guarantee you with probability at least 1 minus delta to find a hypothesis that has generalization error at most epsilon. So you can see that that's the key idea, right? That means, okay, I don't need too many examples. I just need a polynomial number of examples, which are polynomial 2, 1 over epsilon, 1 over delta, the length of feature vectors, and the size hypothesis is H. You just need this order of examples. You can arrive this probability statement defined by epsilon delta. That's called pack learnability. Right? In other words, that means the concept class C can be efficiently learned by your learning algorithm L uses hypothesis H. Okay, we're gonna dive into more detailed discussion on Thursday. Yeah, let's stop here today.